Hi everyone, and welcome to Compliance Panel's live webinar on avoiding statistical pitfalls during method validation. My name is David Benjamin, and I'm going to be a host for today. And on behalf of Compliance Panel team, I would like to say thank you for being part of this event. Now, today's event will be presented by Mr. Stephen Wolfish. Mr. Wolfish is the president of Statistical Outsourcing Services, a consulting company that provides statistical analysis and training to FDA-regulated industries. Now, prior to starting Statistical Outsourcing Services, Mr. Wolfish was the Senior Manager Biostatics Non-Clinical at Human Genome Sciences in Rockville, MD. Mr. Wolfish brings over 20 years of industrial expertise in the development and application of statistical methods for solving complex business issues, including data collection, analysis, and reporting. Mr. Wolfish has been an invited lecturer at Medical Design and Manufacturer, Institute of Validation Technology, and Advanced STAR conferences. Mr. Wolfish has been a speaker at ASQ Division and Section conferences. He's also an editor, board member for Biofarm International, and a regular contributor to the magazine. Mr. Wolfish is a senior manager of ASQ, a certified quality engineer and past chair of the Biomedical Division 2006 and 7. Mr. Wolfish holds Bachelor's of Arts in Statistics from the University of Buffalo, Masters of Science in Statistics from Rutgers University, and an Executive MBA from Boston University. Now, before we begin, I would like to inform you of the program outline for this training session. The webinar is for 60 minutes duration. First, Mr. Wolfish will take you through today's webinar, highlighting the areas that will be covered, and he will then share with you his presentation. We would like to inform all participants that once part of the teleconference have been placed on mute and will remain so until the Q&A session begins towards the end of the webinar. It is for the purpose of avoiding discontinuity and for allowing our speaker to speak clearly so that everyone present can take maximum benefit from this event. We also request all to hold back your questions until the Q&A window begins. 10 minutes of time will be allotted for the Q&A, during which your questions will be answered. Now, if for any reason you get logged out of this training session, I request you all to follow the same procedure to join in again. And now that we're all ready to start, I request Mr. Wolfish to take it from here. Stephen?
Yes, thank you very much, David. A couple of things I'd like to just point out. First, I'd like to welcome everyone to the Avoiding Statistical Pitfalls. You will see that there's a chat box available to you. And the chat box is an opportunity for you during my talk to send questions that you might have excuse me, in a very private manner in which I can then integrate those questions into the training session. If at any time there's something you don't understand, I would advise you to use that chat box because it's a lot easier to answer questions while I'm at the point than it is to wait till the end where maybe your question might not, where it might get lost. So with that, I'd like to get started and give you the agenda for today. What we're going to do is we're going to first start with a basic review of the ICH guideline Q2R1, which is the analytical method validation guideline. And then we'll talk a little bit about the correct statistical methodologies that can be used, talk about a t-test, analysis of variance, or ANOVA. Spend a bit of time talking about regression analysis, some confidence intervals and how you can use those in tolerance intervals during method validation. And then we'll talk a little bit about variance components, which is critical to precision analysis. And then we'll end our talk with sample size analysis for method validation, talking about why a large sample size is just as bad as a small, and then looking at functional requirements to the statistical and comparing them to statistical requirements. So that's pretty much it. It's a fairly packed session. I'll be going at a not too fast of a pace, but I'll pick up some speed at some point. So again, if you get lost or have any questions, please feel free to use that chat box to talk to me and to ask you questions as necessary. So for those that are unaware, there's a ICH guideline, which is the a tripart between Europe, Japan, and the United States for putting together the methodology necessary for method validation. And in that guideline, It talks about 4 different types of analytical procedures: identification tests, quantitative tests for impurities, limit tests for control of the impurities, and quantitative tests for active moiety in samples of drug substances, of drug product, or other selected components in the drug product. We will spend most of our time on the quantitative test. You will see in that guideline that there's actually a grid that tells you what you need to do for each of those 4 different procedures. Since the quantitative test is the most stringent, that's the one we will go through, which covers most of the different tests that are required to be performed. So the first thing that all test methods require is to show that your test is specific, or you have specificity. And in a statistical sense, specificity is the probability that a test is negative given that the analyte is not present. So that is, what is the likelihood that I will get a negative result, or if it's a quantitative assay, that I will get no results or no reading from my assay, given the fact that the analyte that I'm looking for is not present in the sample matrix. So typically what you will do from a statistical perspective is you will take a set of samples that have the that is a neat sample and compare it to one that has the interfering substance that you would be looking for, and showing that, in fact, the interfering substance is not present or does not give a positive result in your assay. So you are basically doing a comparison of the response of the test in the presence of the interfering substance versus when it is not there. And you can do this at a single concentration or multiple concentrations of the interfering substance. That is your own protocol specific. For example, I'll use a medical diagnostic type thing. If you were to be testing glucose in the blood, you might be looking to see if your glucose test is sensitive to the level of cholesterol that might be in the blood. So you might take a sample that has no cholesterol and then spike in different levels of cholesterol and say, okay, my assay is specific to reading glucose and is not affected by different concentrations of cholesterol up until a certain level. And remember, I mean, obviously there's going to be a certain level of an interferent that will start to affect your results. And then as long as you know what that is and can show that, you are able to say that my results are good, provided that my interferent is below a certain level. So, for example, here is a one level of an interference. So the 0, the level of interference substance, the 0 should meet or has none of the interferent, and you might have the interferent at, let's say, 0.25 micrograms per milliliter of the substance, and you would, in this case, test 6 without the interferent and 6 samples with it. The mean of the 6 samples with no interferent is 0.47. The mean of the 6 samples with the 0.25 is 0.51. I get a standard deviation of each of those, and I could do something called the 2-sample t-test and show that with a p-value of 0.07 that there is no effect of the interferent on the assay. And the value that we typically look for is a p-value that is less than 0.05, so this p-value is greater than 0.05, so we say the method is specific to what we're looking for. There's no statistical impact of the interfering substance. You know, one of the questions that I get asked is, so what happens if, in this case, the p-value was, in fact, less than 0.05? And in that case, you would just have to write into your report that, that you need to make sure that the level of the interferent is below 0.25 in order for the assay to be used. This assay is not validated to be used if the interferent is greater than 0.25. That's typically how you would word it. it is not a failure to have an interferent as long as you know that it's there and can control for it in your assay. The second thing that the ICH guideline talks about is linearity. And linearity analysis determines if a linear relationship exists across the range of the assay. Now, linearity does not necessarily mean that you have a straight line relationship, but in fact that you have proportionality, so that the result is proportional to the analyte that's in the assay that you're looking for. So it might not be a linear, it might be an exponential relationship, but if you could transform it back to creating a linear dose response curve, that is the most desirable. So for example, we'll get back to linearity in a moment when we talk about accuracy. The next thing is the range of the assay. And typically there's not something you write into your protocol, so I'm going to evaluate the range. The range by definition becomes the minimum or maximum doses from your linearity protocol that you've tested. So if I test 0, 1, 2, 3 micrograms per milliliter of my analyte and I have a linear relationship, I would say that my assay is validated for the range from 0 to 3. There really never is a range section. It's an outcome of the minimum to the maximum dosage of your linearity. The other thing to keep in mind, and we'll talk about this again with accuracy, is that you must have sufficient precision in that range. So the fact that your assay is linear from whatever minimum to maximum you have, if your precision is poor at any one of those levels, you really do not have a linear relationship. And we'll talk about that specifically when we get to accuracy. So what is accuracy? Accuracy is defined as the difference between the measurement of an individual value and its true value, true but unknown value. So we will test a bunch of samples at a given analyte level. What we believe, now it can be a spiked-in sample, or it could be a WHO standard or a NIST standard or your own internal standard. Whatever you believe truth to be, it is what you observe, how is that different than what you believe to be the true value. There's a concept in the ICH guideline called trueness, which is the difference between the mean of a set of values or the mean of the set of numbers to the mean of the true value. Now, this is a subtlety in the guideline, and I don't want to get hung up on it. Let's just talk about accuracy as just percent of nominal. So I believe that I have a true value, and I spiked in that true value, or I have a true value because it's a standard, and what we want to know is what percent of that nominal value are we. The problem with accuracy is if we do not have acceptable precision, it has no meaning. So accuracy without acceptance of precision has no meaning. So one of the questions that you will ask yourself is, this is a chicken and egg story. Do I do accuracy first, or do I do precision first? And I can't answer that as a universal question. Typically, what I will say is you do your accuracy first, but when you get to precision, as long as your precision is acceptable, then you can accept your accuracy. So you have a contingent, your accuracy is contingent upon your analysis of precision. And we will see a way for us to be able to analyze that clearly throughout the process. So here's an example where I have actually 4 different runs for 3 different analyte levels. I have it 80%, 100%, and 100%, 120% of the assay, of the analyte level that I want to test my assay. So my range is from 80% up to 120%. The input amount in milligrams is how much I put into each sample. So the low 80% has 117.62 milligrams. My nominal amount is 150.43, and my 120% is 181.88. This data comes from a test where I have 150 milligram label claim. I want to make sure that my assay has a range for being able to be used for both stability testing, acceptance criteria, acceptance testing, and maybe other in-process testing. So I want to validate my assay from 80% of nominal up to 120% of nominal, or 117 up to 100, or 118 up to 182 milligrams. When I did that, I have the third column, which is the amount found. That is, what does the assay tell me? So for the 80% in run 1, it told me I had 115.33 and 116.53. And then the final column gives me the percent recovery. So the 115.33 is actually 98.05% of the target amount. Now, by using percent, it allows me to combine the three samples into a single analysis as such. The first thing is I could take all 24, so that's the 4 runs, 2 reps per run, 3 different levels of condition, 24 total results, and say my average percent recovery was 99 point, and I'm going out to an awful lot of decimal places in an example. You don't need to do that. 99.7% recovery with a standard deviation of 1.28, and my RSD or CV is about 1.29%. That's the overall recovery. I don't necessarily want to only report the overall recovery. I want to look at it each of the 3 analyte levels. So the 80% sample recovered at 99.07, the 100% sample recovered at 99.91, and the 120% sample recovered at 100.08. Now, one of the things that you'll ask yourself is, it looks to me as though the percent recovery is increasing as I increase in analyte levels. So I'm starting at 99.1 to almost 100% to about 100.1%. And you're going to, want to know, is that statistically significant? And we'll take a look at how we could assess that. But this is the first step in doing accuracy, is to say, I've got the recovery at 80, at 100, and 120%. The next thing you're going to do is some sort of regression analysis or some sort of analysis of variance. And we'll talk a little bit more about this methodology in a moment. But here what we're doing is we're saying, and the bottom box is the key, we're saying if we fit a linear regression model to the 24 values where we put 80, 120, 80, 100, 120 on the x-axis, and we look at the percent recovery, we would expect to see a, well, let me see, this here. I put 80, 100, 120 on the x-axis, and I look at the recovery, we would expect to see a relationship of 1. That is, as I increase linearly in my amount of dose in milligrams, I'd expect my response to be a 1-to-1 response. Here it says that we have about a 2% bias because our estimate is 1.019, so about 1.02. So we are looking at about a 2% bias. That is, for every 1 milligram that's in my sample, I'm reading 1.02 milligrams on the response, on average. You have an intercept that tells you what exactly is the place where if I had 0 analyte, what would my assay say? So in this case, it says if I had 0 analyte, I'd actually have a negative 3.25 reading. Now, if my assay is not going back down to being able to test things at 0, again, I'm looking at an assay that goes somewhere from 117, 118 or so up to 180. I don't care the fact that at 0 it crosses the y-axis at a negative number. What I care about is the slope is close to 1. And as long as I can show that my slope is close to 1, and in this case, I'm showing that my intercept is negative 3.25, actually the p-value associated with it, the last column, shows that it's not even significant. So You could, at this point, do an analysis such that you actually remove the intercept. I'm not going to get into a no-intercept model at this time, but you could do that. What's important in this analysis of accuracy is to try to show that your estimate of slope is close to 1, if possible. What we tend to do in statistics is build confidence intervals around parameter estimates. This is building a confidence interval about both the slope and the intercept. So the top is the intercept, and the negative 3.248 was our estimate of the intercept. The 2.2589, if we go back, it shows you the standard error of the estimate. So you're going to take the estimate plus or minus the standard error times a t-value associated with the degrees of freedom. In this case, it's 2.074. What I basically have done here is created a 95% confidence interval around the intercept value. So if I was to do this study 100 times, 95 out of 100 times, I would expect my intercept to be anywhere from negative 7.9 all the way up to 1.44. And as you can see, the value 0 is contained in that interval, which means, as we saw previously here, that the intercept the p-value was 0.1646, which means that it's not significant, which means it's not different than 0. The confidence interval, because it includes 0, says that 0 or a no intercept or the regression line would fit and go through the origin is a possibility. So that's the first thing I want to be able to assess. The second thing is a 95% confidence interval on the slope. If I look at the 95% confidence interval using the same logic, 1.019, which is the actual slope plus or minus the standard error, 0.0148 times the t-value of 2.074, I will find that my 95% confidence interval on the slope is 0.988 to 1.05. The value 1 is in that interval. So here's a way for me to show that, in fact, the slope is not statistically different than 1. So remember, here when I look at the fact that my p-value is less than 0.05, it says here it's less than 0.001. That's testing if the slope is statistically different than 0. And clearly it is statistically different than 0. That means we have a dose response curve. But if my hypothesis is that my slope is not different than 1, this confidence interval gives me that ability because it says that 1 is a possible value for the slope. So I can make a claim that my slope is not statistically different than 1. Now, by using these two sets of confidence intervals, I can actually look at accuracy and my assessment of linearity in one basic model, and that's this particular grid, because the level that I spiked in is 120, 150, and 180 milligrams. Now, you know, it's not always going to be perfect, so I got that 117 and change. I had 150 and change, 180, you know, a little different 180. So my spike in was 120, 150, 180. Based on the statistical model from regression, I get a predicted value. The confidence intervals that we just saw, we can build a predicted value for each of the 3 levels. I can look at my difference from theoretical, that is just the confidence interval minus the spiked in level, and then I can convert those into percentages. And by doing that, what I've basically said is that this assay says that I'm 95% confident that the bias is no larger than 1.8%. So I'm no worse than at any point from 120 to 180, the range of my assay, I'm no worse than 1.8% bias from what the true value is. So in the essence, what we can say is that this assay has a no worse than a 2% or 1.8%, however many significant digits you'd like to discuss, we're basically no worse than 2% bias. Again, that's half the problem. We still have to assess the precision of the assay in order to have any understanding of if these values have meaning. So let's talk about precision. The guideline really breaks precision into two parts, intermediate precision and repeatability. And let's talk about what repeatability is first. Repeatability is taking the exact same sample and measuring it over and over and over again. So if I took the same sample, measured it 10 times, the variability of those 10 readings is my repeatability. The intermediate precision is all of the other things that could affect the assay precision. That would be operator to operator, day to day, run to run, lot to lot, if you're looking at different lots of reagents. That is all captured in intermediate precision. The only thing that is not an intermediate precision, it actually has its own topic in the guideline, is the lab to lab, and that's called reproducibility. And this would be is if I ran it in my QC lab, and then I also want to run this assay in my R&D lab, that would be reproducibility. Now this is really, precision is really the place where statistics has its greatest impact, because typically your precision analysis and precision protocol is going to be some sort of statistical design, an experimental design. We're going to use something called variance components as well as summary statistics. So it has the greatest area for statistical rigor in all of the ICH guidelines. The next couple of topics in the guideline are things that I don't see as huge statistical applications, but they are things that you tend to have to report out. The first being your detection limit, which has several different ways to be calculated. The first is to take 3.3 times the standard deviation over the slope. The sigma and the slope are from your calibration curve. If you're not using a calibration curve, you can just do the detection limit by taking a blank sample, measuring it 10 times, and then taking 3.3 times the standard deviation of those 10 values, and that's your detection limit. The detection limit, by definition, is the lowest analyte concentration that you get a response that's different from the background, but you might not necessarily be able to quantify that response. Which leads us to the idea of quantification limit, which is 10 times that standard deviation. And the quantification limit is the lowest analyte limit that I can not only differentiate from the background, but I can quantify it with acceptable precision. And so detection limit and quantification limit are basically just plug and chug straight formulas. It's the same set of data, the same 10 results, same 10 blanks that you're going to run. One is 3.3 times the standard deviation. The other one is 10 times the standard deviation. If you understand that this conceptually, the detection limit is always going to be 1/3 that of the quantification limit, or the quantification limit is 3 times the detection limit by the definition in the guideline. There are many ways to do detection limit. There are many ways to do quantification limit. You can go back to the guideline. Most people have their own way of doing quantification and detection, have their own definition of it. It's open to the most interpretation, because depending on what assay you're doing and what assay you're validating, detection, quantification limit have different meanings. Some people have a lower level, the low limit of quantification and the upper limit of quantification, because you might have some hook or some other thing going on in your assay that says, I can't only assess the lower level, I have to also assess the upper level for quantification. So I don't want to spend too much time on this, given I'm limited to 1 hour of time. but keep in mind that it's pretty much just a plug-and-chug formula for those. Okay. So what happens, though, so that's pretty much the ICH guideline. I try to touch upon the the high points of the guideline, but what happens if I have more than two levels that I want to compare? And this is, let's go back to the specificity. Remember in specificity I said I had a 0 and a 0.25. If I wanted to compare more than just those two levels, let's say I want to do a 0, a 0.25, a 0.5, 0.75, 1, I need to start to use a different method than a t-test. I can't just use a t-test to compare two means. I have to now use a technique called analysis of variance. And typically, most software has the ability to do the one-way types of analysis of variance. So we'll talk a little bit about that. Typically, what you'll do is a t-test. A t-test is the following general formula. You'll have x bar 1, which is the mean of one sample, and x bar 2, which is the mean of the other. So x bar 1 could be the mean at the 0 concentration. X bar 2 would be the mean at 0.25. You divide that by the square root of the variance from the 0 over the number of samples plus the variance of the 0.25 over the number of its samples. This test does not require you to have an equal number of samples at 0 and at 0.25. And this is important because sometimes, because you want to do detection limit and quantification limit, you might do 10 samples. You might want to combine quantification, detection, and specificity. So you might do 10 samples at the 0 level, but only do 5 at each of the different spiked in analyte levels. And that can be done using this t-test formula in order to assess if my interferent level is statistically different than my neat or 0 level. What we will do is we will look at this formula, and when we calculate it through, we get this value called T. So T would be the product of x bar 1 minus x bar 2 over the square root of the variance of 1 over M1 plus the variance of 2 over M2. And if, in fact, the observed value from the formula exceeds the tabled value, then the two means are considered statistically different. And if we have more than two levels, we do not want to do all of the different t-tests, which is typically what will happen. When I look at and working with clients about method validation, the number one thing that I will say is people will test 0, 0.25, 0.5, 0.75, and 1, let's say. They'll do a t-test to compare 0 to 0.25, 0 to 0.5, 0 to 0.75, 0 to 1. We don't want to do that. We want to use this technique called analysis of variance to see if, in fact, any of the means are different than 0. The analysis of variance in general is a technique that looks at the variability between the different factor levels and compares it to the average within factor level variance. So I can take, we'll take a very simple example. I take 5 replicates at 0, 5 at 0.25, and 5 at 0.5. I'm going to get 3 different variances, one for 0, one for 0.25, one for 0.5. I'm going to also get 3 means. So I can take the variance between the 3 means and take the average variance of the replicates. And as long as the variability I see within a particular level is not significantly less than what I see between the levels, I will conclude that the different levels are not statistically different. So again, what we're doing is we're comparing the different concentration levels, and our hypothesis is that there's no difference amongst the concentration means. The problem with ANOVA is it's an omnibus test. It just tells you, yes, you have differences, or no, you don't have differences. It doesn't necessarily tell you what those differences are. And that becomes a little bit hard for us to deal with. And so you have to use something called multiple comparisons to determine if, in fact, the differences that ANOVA tells you you have are differences amongst the 0 level and the spiked-in level, or if the differences are between 2 of the different spiked-in levels. ANOVA also will allow us to determine if our error that we're saying is systematic error or if it's random error. Random error means that I just have a repeatability problem. There's just too much variability within a given analyte level. Systematic error means that I am getting differences amongst my levels, that the response is statistically different between 0, 0.25, 0.5, 0.75. And you use the ratio of these mean squares in order to get to that. So typically, this is what you would see in an analysis of variance table. And I built this up backwards for a purpose. But the top is the total variability. The middle row is the error or the repeatability piece of it. And then the bottom is the model or the intermediate precision piece. And what we're going to compare is the variance, the mean squared of the model, statistically different than the error term that we have. The key thing about analysis of variance is that the mean squared error is a variance that tells you what is your repeatability. So if I wanted to, I can take the square root of the mean squared error, and that is my estimate of repeatability. Okay. So let's look at a real example, because it's a lot easier for us, more tangible for us to look at an example for looking at how ANOVA worked. Imagine that we had 3 different levels, level 1, level 2, level 3. And it doesn't matter, you can call level 1 the 0 and level 2 0.25 and level 3 0.5. For this example, it doesn't matter what the actual concentrations are of the 3 levels. But understand I have 3 different levels. And for each of the 3 levels, I can get a mean. So the average value for level 1 is 99.8, the average for level 2 is 101.3, and the average for level 3 is 104. If I was to do the multiple t-test approach, the thing I would do is, first thing is I would do a t-test comparing level 1 to level 2, and so 99.8 compared to 101.3 says that my p-value is 0.482, not statistically different because it's not less than 0.05, so there's no difference between level 1 and level 2. I then go on and do a comparison of level 1 to level 3. Exact same thing where 99.8 is compared to 104. I use that t-test formula. I find out my p-value is 0.046, and I would conclude that level 1 is statistically different than level 3, that 99.8 is, in fact, statistically different than 104. And then the last comparison that one would do is 2 versus 3, 0.482, and we would say that those are not different. So if I did the 3 different t-tests, the conclusion that would be reached in this approach is that level 1 is different than level 3. But if you look at the first bullet point, when I used analysis of variance, the p-value is 0.1799. So that would have concluded that there is no statistical difference amongst the levels. Statistical mumbo-jumbo, people are saying. Because I know that, I mean, when you look at this, you go, well, what's the right answer? If I use analysis of variance, it's going to tell me there are no differences amongst the levels. But if I use the multiple t-test, it's going to tell me that level 1 is different than level 3. So which is the correct approach? The ANOVA approach is the correct approach. If you do enough t-tests, let's just take a second to understand p-values and what they're telling you. A p-value, we say that if the p-value is less than 0.05, it's statistically significant. A p-value of 0.05 exactly says that we would have observed the difference that we did between these means by chance alone 5% of the time. So we say that, hey, if the likelihood of seeing this by chance alone is less than 5%, it must be, something must be going on. There must be a statistical difference. If you do enough of these t-tests, by chance alone, you're going to find a difference amongst the levels. Analysis of variance says, I don't know which levels are going to be different. If they're different, I just want to test if any levels are different. And in this case, the ANOVA says, nope, there is no difference amongst the 3 levels. So you want to use this approach to conclude at the end of the day that level 1, level 2, level 3 is not different. Now, let me kind of make something very clear. Typically, when I give a long one-day talk on statistics, I usually open up with one of my favorite quotes, which is, "There are lies, damn lies, and statistics." I can use ANOVA here, and if I specify it in my protocol, because that's what you need to do, is to specify in your protocol what analysis method you're going to use. If, in fact, I use ANOVA, I am going to, in most cases, not find differences that if I would have done multiple t-tests, one of those multiple t-tests would have shown a difference. So you want to use ANOVA because it is the one that's going to give you the best chance of not seeing differences amongst your levels. And depending on your protocol, I'm going to usually go out on a limb and say, typically, you do not want to see differences amongst your levels, so ANOVA would be the most appropriate method. So let's start to walk ourselves through regression analysis and how to use regression analysis in our final about 10 minutes of my talk. In regression analysis, what we're going to do is get two parameters. One is the slope, one is the intercept. And typically, what we want to know is if the slope is significantly different than 0. A slope that is of 0 would indicate there is no relationship between x and y. So if I'm trying to do linearity or accuracy assessment, I want to make sure I have a slope that's statistically different than 0. That is, as I add more analyte, I hope my response from my assay is, in fact, not going to be a flat line, but it's going to be proportional to the amount I put in. The intercept also is tested to see if it's statistically different than 0. And an intercept of 0 would indicate that the regression line passes through x equals 0, y equals 0. An intercept of 0 is equivalent to saying the regression line passes through the origin. Now, I said before that if you use regression, you get a intercept that's not statistically different than 0, you could use something called a no-intercept model. I am not going to say that that's the right thing to do. At the same time, I won't say it's the wrong thing to do. Typically, I say don't do it unless you know for sure that you want to do testing very close to 0. Because the intercept has no meaning if my assay is used from 100 to 1,000. Who really cares where the line crosses at 0? Because I'm not going to test samples down at that level. But if I'm going to start testing samples very close to 0 or at 0, then I want to know that my regression line passes through the origin because it's important for me not to have a bias at the low end. Some of the assumptions of regression. The first thing is that errors are independent normally distributed mean equal to 0 and variance of sigma squared or s squared. Basically, we want to know that every sample, its difference from the mean would give me a normal distribution. So if I took the difference amongst the observed and the predicted, that distribution is normally distributed. It's not an assumption that most people are going to check. I don't want to talk an awful lot about it because typically most people, when you have a linear regression model, have a normally distributed set of data. If you don't, regression is not the right technique. The second assumption is that X values are known without error. This is typically violated almost every time you do an analytical method validation because you don't always know X without error. Most of the time, samples are prepared, and so you spike in a known concentration. Well, when I say I spike in 150 milligrams, is it exactly 150.000000? Nope. There's going to be some error in my value. I assign it a value of 150, but the truth is it might be 150.000362, whatever it's going to be. So again, intrinsic, the X value needs to be known without error. As long as the errors are really small, it's a small impact on the regression analysis. The third is the relationship needs to be intrinsically linear, which means that if I can't get a linear relationship, I can transform my data and make it linear. We need for us to be able to use regression in a linear model. And the last is that errors are constant over the range of X. And this basically says, and this is another one that gets violated a lot, that as my analyte concentration increases over time, that in fact my variability doesn't increase. Typically it does. As long as that variability increase is not significant, it's not a big issue. A couple of the hazards of regression: it's inappropriate to extrapolate around the range of X, but if you actually did stability analysis, it allows for it. And the rationale behind that is that they have a caveat that says you can't just extrapolate forever. It says you can basically extrapolate twice the last data point you observed. Regression is not built for extrapolation, but under certain circumstances, it's the best you can do, so you extrapolate. The second thing is that influential observations or outliers can give misleading models. You have to do some sort of analysis, like residual analysis, to make sure that you don't have any influential observations. The way influential observations appear is you might start at, let's say, 1,000 milligrams. I want an assay that has a range from 100 to 1,000. So I do 1,000, 500, 250, 125, and down. Well, the impact of 1,000 milligrams is going to be great because the next closest sample is 500 milligrams. So I'm in essence extrapolating between 500 and 1,000 and making a linear line. So the line is going to be fit to the most influential observation, which in this case would be the largest observation. The last hazard of regression here, the regression of y equals x is not the same as the regression of x equals y. The problem is this is the cornerstone of most analytical methods. Typically what we do is we spike in an analyte level, we get a response. We then use algebra to find out that in the future, I'm just going to get a response. I need to figure out what is the concentration of that response. So I use algebra and I make my y equals x relationship into an x equals y. I don't want to get into a lot of talk about this. It's the cornerstone of analytical methods. It's what's done. The assumption here is that you have no error in your model. It's not the most statistically valid thing to do, but it's the bread and butter of how we do analytical method and assign a dose to a response. Suffice it to say, it gets done and there's nothing we can do about it. The last couple of points I want to make, how good is the fit? You want to use something called R squared. Now, I'm not a huge fan of R squared. I think that most people overuse it. They will have an acceptance criteria that says R squared has to be greater than 0.99 or 0.98. It's really not a good acceptance criteria. R squared tells you what percent of the variability is explained by the model, but it's a highly, highly influential concept, and I'm going to touch upon that in a minute. The other thing is you want to test if any of my assumptions are violated by using residuals. And then the last thing is the linear model even appropriate, and using something called lack of fit test. The famous Anscombe data set basically says that there's a data set that says, okay, look, I've got 4 different Y values, the last four columns, Y1, 2, 3, and 4. And all 4 of them have the exact same mean, 7.5, and all 4 of them have the exact same standard deviation of 2.03. But what I'm going to do is I'm going to have 4 different X's. X1, X2, and X3 are all exactly the same. But X4, he basically said it's a bunch of 8s, and there's 1/19. And if you took the average of the first column or the average of the second, they too have the exact same mean. These are the 4 different graphics that you can get. X1 versus Y1, X2 versus Y2, X3 versus Y3, and X4 versus Y4. And if you fit those, take that data set and fit the 4 models, you will see that in the first one, X1 versus Y1, it's a pretty normal regression model. The second one, X2, is a curvilinear relationship. X3 has 1 influential observation that pops out, and X4, all of them were at 8, one was at 19, so that's an influential observation. But ironically, if you look at the regression, all 4 of them have the exact same R squared, and all 4 of them have the exact same regression. So you cannot apply regression blindly. you have to be able to look at the picture, because the only one of these four that actually is the correct usage of regression is X1 versus Y1. So we don't want to blindly apply regression analysis to our data, be it for linearity, for accuracy, without first plotting the data to make sure, in fact, I don't have influential observations, I don't have any outliers, I don't have a curvilinear relationship, but in fact I have a normal scatter of my data points. R squared, as I said, is the percent of the variation explained by the model. Unfortunately, as you can see from the Anscombe data set, it's very sensitive to data distributions and spread. A high R squared does not necessarily mean that it's a good fit. A residual is just a difference between the observed value, yi, and the predicted value, yi hat. And what we want to do is we want to take these residuals and plot them. And when I plot them, I want to be able to see if I have normal scatter. One of the things that I like to do is something called a standardized residual. I take those residuals, I divide it by the square root of the mean squared error. By doing that, I standardize my residuals on an average of 0, because the sum of the residuals is 0, and my variance becomes 1. Now, if I have a standardized residual that is greater than 3 or less than -3, I can use that as an assessment of, do I have outliers in my data set? Again, residual plots, that's plotting residuals versus the X values, allows me to assess how good the model is. It allows me to look to see if my regression function is linear, if I have that constant variance, if I have error terms that are independent, if I have any outliers. And typically, you'll see one of these 4 different patterns. The upper left, the normal pattern, is I just have normal variability of my residuals amongst the line, which is y equals to 0. If I get a curvilinear relationship, the upper right-hand corner, that would be like in the Anscombe database, the y2 by x2. That means I need to do some transformation of my data set because I don't have a linear relationship, but I have some sort of x squared going on in my data set. So typically, you'll take the square root of the x's or square root of the y's to normalize that data. The bottom left is the most widely seen pattern, and that is where you start to see an increase in the residuals as my analyte level increases, or sometimes it'll go the other way. You'll have the highest variability at the low level, and it'll start to come down. In this case, you need to find some sort of transformation of the data to try to get yourself back to a normal pattern. The last one is a time effect. If you plot your residuals versus time, so you look at the time of, the order in which the results were generated. If your residuals are increasing or decreasing over time, then you did not randomize your study sufficiently, and you have a time effect going on. Just want to talk about precision analysis. Repeatability is the measurement of the same sample multiple times, where intermediate precision is all of the other sources. We use something called variance components or decomposition of the variance. It allows us to assess intermediate precision versus repeatability. Reproducibility, as I mentioned, is lab-to-lab variability. I personally add that into the intermediate precision. If you're going to do it, put it in your protocol. Put it in the protocol that you're going to do intermediate precision, and it's going to include day-to-day, lot-to-lot, lab-to-lab, operator-to-operator, whatever it's going to be. Your protocol determines what is, in fact, your true reproducibility or intermediate precision, not some statistical mumbo-jumbo. In the protocol, you say, these are the things I'm putting into intermediate precision. The repeatability is always going to be the error of the model. My suggested study for precision analysis is, if you're going to do it, you want to use a minimum of 2 analysts, a minimum of 2 days, a minimum of 3 replicates at a minimum of 3 different concentrations, and then you can build this variance components model that will look something like this. So here you are going to look at the analyst in the day as the intermediate precision. The error term, that epsilon at the end, is going to be your error, and then every model has an overall average. just to talk quickly about the idea of tolerance intervals. Tolerance intervals are really a very powerful thing because it allows me to look at the distribution of the individual values, not the distribution of the mean, but it's the distribution of the individual values. So here it will tell you what percentage of the population will be contained in that interval. It has two things. It says, typically you'll say I'm 95% confident that 95% of the individual values fit inside of this tolerance interval. These K values are contained in an ISO standard, and then it's also in the NIST handbook that's online. So if you Google NIST engineering handbook, it gives you the formula for calculating these K values. I'm running low on time, so I'm just going to cover the last couple of slides a little quickly. This is the type of errors that you run into when you do method validation. You basically can make a correct decision if your hypothesis is in fact true and your sample tells you you're true, you made a correct decision. And if you should have rejected your null hypothesis and in fact you rejected it, that is a correct decision. The two errors that you run into, though, is type 1 error, or this alpha we've been talking about, and that is when I reject the null hypothesis when it is true. So in fact, I conclude that the two means are statistically different, but in reality they're not different. That's a type 1 error. The other error you make is type 2, which is called the beta error, and that is where I accept the null hypothesis. So I say that the two means are not statistically different, but in reality they are statistically different. And during validation, the type 2 error is more important than the type 1 error, because in the essence, what we will do is we will conclude that our method is in fact sufficient for its intended use, when in reality it's really not. So we want to be cognizant of our type 2 errors that we can make. And the last piece of this is statistics doesn't answer everything. And because of that, there are times when you will conclude statistically that things are different, or you will conclude that things are not statistically different because the errors are either very large or the errors are very small. So what you want to do is you want to always specify something called an equivocal zone, which says that even if I'm statistically different, if the difference amongst my means is small enough, I'm not going to conclude they're different. And in scenario 1 and 4, both the equivocal zone and the statistical test were in agreement. In scenario 2, it's where the precision is so good the statistical test fails, though the practical sense is similar to the target. So scenario 2 would be where I would conclude statistically that the means are different, but the difference is small enough that it's not clinically relevant. I don't want to conclude that they're different. The difference is just not meaningful enough. I'm going to conclude that, in fact, they're not different. Scenario 3 is the one that gives us the most confusion, because here, statistically, I'm going to say I'm not statistically different, but in fact, the variability is so large that, in fact, it's possible that I'm going to get outside my equivocal zone. So sometimes doing no statistical analysis is better than doing the wrong statistical analysis when it comes to method validation, because you can make type 1 and type 2 errors that can make the wrong conclusion. Sometimes statistical methods might get called down in some regulatory document, though typically they don't do that. Typically they just say assess linearity, assess precision. They don't tell you how to do it. And so it could be, well, it could be misunderstood, or more importantly, it's just confusing. And hopefully, in the last hour I was able to give you some techniques for doing the analysis so that you have a well-understood method. But before you do any data collection, make sure you specify in your protocol what is the data methodology the data analysis methodology you're going to use. Pre-specify it, because you don't want to do data dredging. You want to make sure that you're assessing your precision or your accuracy in the correct fashion before you even start collecting data. So I'm going to open it up to questions at this time.
Stephen, thank you very much for the wonderful presentation. And I would also like to thank all participants for cooperating with us. It is now time for the Q&A to begin, and we request all who have questions for a presenter to click on the raise hand option, which is a palm-like icon at the bottom of your participants panel, to ask your questions verbally or post your questions in the Q&A panel so that a presenter can read it aloud and then answer. For any reason, if you're unable to ask your question either by the two means I mentioned, you could share it with me, your host, by chat, and I shall pass it on to a presenter to answer it. Meanwhile, we sincerely request you to share your feedback in the feedback form, which will appear on your screen in the polling window right now. The feedback form is just 6 questions, mostly multiple choice in nature, and wouldn't take more than 2 minutes to answer. And ladies and gentlemen, as I mentioned, you could either use the raise hand option, which is below the participants panel, to ask your questions verbally, or post it in the Q&A panel, or send it to me by chat. Stephen, I don't see any questions coming in. Could we go to the question with your permission? All right. Would you like to send
if any questions do come in, I still send them to you, David, and feel free to forward them along to me, and I will be more than happy to answer anyone's questions at a later date.
Thank you very much, Stephen. And ladies and gentlemen, we're very grateful for you having taken part in this webinar. And if you'd like to get in touch with us, you can send us an email to webinars@compliancepanel.com. And if any of you feel that you and your team members would benefit from this webinar, we'll be happy to inform it. It will be available in the recorded format and can be purchased from our website, or you can call us at 800-447-9407 or 714-441-5856. We welcome your suggestions and feedbacks or ideas on how we can improve our webinars. If you'd like to suggest a topic or desire a customized corporate training on-site or online, we ensure that whatever is your training necessity, it will be our priority. And we look forward to having you with us again sometime soon and for your continued patronage. Now, on behalf of our presenter, Mr. Walfish, and the compliance panel team, I would like to say thank you for participating in this webinar, and we wish you a pleasant day ahead.